Hello and welcome. In this video and in future videos to come, we'll be taking a look at several different methods for determining whether or not a series converges or diverges. Now, in a previous video, we saw a really good example called the geometric series, and we know that it converges when that ratio is between -1 and +1, and it diverges in all other cases. But the nice thing about that geometric series is actually when we know that it converges, we can use a formula to calculate the actual sum of that series. Now, we're not going to be quite so lucky with this video. We're going to be taking a look at just determining whether or not a series is convergent, whether or not its sum is finite and it gets closer to it, or whether those partial sums get closer to the value, or whether it's divergent and it doesn't make any sense, or maybe the sum is infinite. So it's a little bit different take on series. What are we going to do when we see something that's not geometric? Well, let's start off with the easiest kind of case. We can very quickly find out when a series is maybe divergent. So we've got the test for divergence. The test says that if we take the limit of our terms, an, as n goes to infinity, and find out that that limit either does not exist or does not equal 0, then the sum of those terms is divergent. And hopefully that kind of makes sense. When we want a series to be convergent to some value, that means our partial sums need to get closer and closer to some value. And we're really thinking about the limit of the partial sum Sn, as n goes to infinity, has to equal some number. Well, that's only going to be true if each new term that we add to the partial sum is going to get smaller and eventually approach 0. So let's just see if we can find an example of a series that we know for sure is going to be divergent. Here we've got a series from n equals 1 to infinity, summing the terms 2n squared over 3n squared minus 1. Now you'll see here that it's not a geometric series. There's no common ratio, and geometric series typically have some sort of constant to the power of n, and these are in fact just powers of n. To test whether or not this is convergent or divergent, we could take a look at the partial sums and see if we can come up with a formula for the nth partial sum and take the limit as n goes to infinity of that expression. But it might be a little easier just to see what happens to these terms as n goes to infinity. In this case, the nth term in our series, an, is equal to 2n squared over 3n squared minus 1. Let's see what happens to that as n goes to infinity. Taking the limit of 2n squared over 3n squared minus 1 as n goes to infinity, there's a couple things we could do. We could apply L'Hopital's rule, or we could go and divide by the highest power of n in the denominator. Why don't we use L'Hopital's rule? Taking the derivative of the numerator, we have 4n, and taking the derivative of the denominator, we have 6n. Let's see about this limit now. The limit of 4n over 6n as n goes to infinity, well, the n's cancel, and that leaves us with 4 over 6, or simply 2/3. Well, this means that by the test for divergent, this is a divergent series. But let's see if we can try to make a little more sense of that result. When n equals 1, we have 2 over 3 minus 1, which is equal to 1. When n equals 2, this gives us 8 over 11. When n equals 3, 9 over 13. When n equals 4, 32 over 47. Now, what's not immediately obvious until we maybe start getting closer to, I don't know, maybe the 10th term or so, when n is equal to 10, this is 200 over 299. And you see how close that is to the fraction 2/3. And essentially, all of the terms after that are approximately equal to 2/3 each. And if we add 2/3 plus 2/3 plus 2/3 forever, we know that this must be an infinite value. This can never be a finite value, so therefore, this series must be divergent. Now, the test for divergence is fairly straightforward. It is just a matter of finding out whether or not the terms themselves go to 0. If they don't, it's divergent. But what about trying to find out if a series is convergent? Well, then the test for divergence doesn't help us out with that. Let's see one example of how we can test to see if a series is convergent by using integration kind of as our main strategy. The integral test says that if f is a continuous positive decreasing function over the interval from 1 inclusive to infinity, and if each term in our series can be written out as just f of n, then that series is convergent if and only if the improper integral from 1 to infinity of the function is convergent. That means that if we are looking at this function f and find out that its improper integral from 1 to infinity is convergent, then so is the series. And if the improper integral is divergent, then again, so is the series. To better understand the integral test, let's take a look at an example and see how the integral test is sort of like a visual representation of a series. The harmonic series is a pretty classic example of series. It's simply just the sum from n equals 1 to infinity of 1 over n. So this gives us 1 plus a half plus a third plus a quarter plus a fifth and so on, the nth term just being 1 over n. Now, is the harmonic series convergent or divergent? Let's use the integral test here and then sort of see what that gives us as a visual representation. Well, here our nth term is 1 over n. If we want to write that as a function of n, then we could say that an is f of n, where the function f of n equals 1 over n. Now, before we dive into the integral test, there are the three hypotheses that we have to double check. We need to double check and see whether or not this function is continuous from 1 to infinity, which it is. We need to double check and see whether or not this function is positive for all values from 1 to infinity, which again it is. And we need to double check and see whether or not this function is decreasing from 1 to infinity. And we can very quickly do that by taking a look at the derivative. And the derivative, f prime of n, is negative 1 over n squared. And that is always less than 0 for any value of n not equal to 0. So we also know it's decreasing. That means we're going to take a look at the definite integral from 1 to infinity of f of x, well, that would just be 1 over x with respect to x. And treating this as an improper integral, type 1, we're going to replace infinity with t and take the limit as t goes to infinity. And integrating 1 over x gives us the natural logarithm of the absolute value of x, and then we'll evaluate from 1 to t and take the limit as t goes to infinity. Now the absolute value of t is just going to be t, since t is already greater than or equal to 1. So that'll just be the natural logarithm of t, and the natural logarithm of 1 is 0. But the natural logarithm of t, as t goes to infinity, gets infinitely large, so this limit does not exist. It equals infinity, which means that by the integral test, the harmonic series is divergent. Perfect. We know the harmonic series is divergent, but let's see if we can try to explain a little bit more about why that is the case. And to visualize this, I'm going to use Maple. All right, well, here in Maple, I've just used the Calculus 1 package from the student suite of packages, and I'm using the approximate int command just to be able to help visualize this sum. And you can see that I've got that function 1 over x, and these bars here, you can see have a width of 1. And look at these values for their heights. At n equals 1, we have 1. When n equals 2, we have a half. When n equals 3, we have a third. When n equals 4, then we have a quarter. And so this is 1 plus a half plus a third plus a quarter plus a fifth plus a sixth and so on. And this actually is the harmonic series if we were to add up all these blue bars. Now I can't go to infinity, I've just stopped at 10. But we know that the area under the red curve here is infinite. It does not converge because we've just done that with the integral test. And well, all of these blue bars here, you can see that their areas are actually just slightly larger than the area under this curve, starting at n equals 1 going up to infinity. So there's no way that the sum of these fractions can possibly be finite when their sum is slightly larger than the area under the curve. So that is where we can say that by the integral test, the harmonic series must be divergent. All right, let's take a look at another example that's pretty classic. Let's take a look at the p-series. P-series is any series of the form 1 over n to a power p. So it's not geometric, and you'll notice already that when p equals 1, this is just a harmonic series, and we know that is already divergent. But when is a p-series convergent? And can we find out when, in general, it is divergent? Well, let's take a look at that integral test again. Once again, we can write each term as a function of n, where that function is 1 over n to the p. Let's double check those three conditions. For any values of n greater than or equal to 1, this is definitely continuous and positive. And what about decreasing? Well, the derivative of this would be negative p over n to the power p plus 1, just using the power rule on n to the negative p. And you can see that that is decreasing whenever p is positive. So that meets that third criteria. And we can take a look maybe at what happens when p is negative in a moment. Let's try the integral test now. We'll be taking a look at the improper integral from 1 to infinity of 1 over x to the p. Now, the moment that we write down this improper integral of 1 over x to the p from x equals 1 to infinity, you might remember that we've seen this before. In a previous video on improper integrals, we know this is convergent only if p is greater than 1. We also know it's divergent if p is less than or equal to 1. So that tells us this p series is convergent when p is greater than 1. By the integral test, that tells us that this series is convergent for p greater than 1. We also know it's divergent for p less than or equal to 1, but we haven't been able to use the integral test when p is negative. Let's just take a moment and see what happens if p is negative. If p is less than 0, we might want to write this series as n to the negative p. But because p is negative, negative p is positive. And taking the limit as n goes to infinity of n to a positive power, well, that is going to be infinite. That's going to continue to get larger and larger. N to a positive power is going to get bigger and bigger. So by the test for divergence, we know that this series, this p series, is divergent whenever p is negative. So with the integral test and the test for divergence put together, we know that this p series is convergent for p greater than 1, and we have divergence for p less than or equal to 1, including all of the negative numbers, where it's going to be divergent just because of the divergence test. Now, these are a couple sort of famous examples, harmonic series and p series, and we'll see those again many, many times. But essentially, you should probably try the integral test anytime if you're taking a look at a series that may be convergent, because you can't obviously tell it's divergent. It seems like the terms are going to 0. Worthwhile to try it out as long as it looks like a function that you can easily integrate and apply your techniques from improper integrals. Let's take a look at the series from n equals 1 to infinity of 4n over 2n squared plus 1. It looks like something that we could easily go and integrate, but we just want to make sure that we always have the conditions being met. As before, this is continuous. It's positive. It may not be quite as obvious to see whether or not it's decreasing, though. To get the derivative, use the quotient rule, and then if you want to factor and simplify, then we end up with negative 4 times 2n squared minus 1 all over 2n squared plus 1 squared. Let's see, when is this going to be negative? Well, we always know negative 4 is negative. We always know the denominator is positive. So as long as 2n squared minus 1 is positive, this would be a negative derivative. To have 2n squared minus 1 greater than 0, then we need to have 2n squared be greater than 1, or n squared greater than 1/2. With our series, n starts at 1 and continues to increase, so this is definitely always going to be true for any value of n from 1 to infinity. So we know that this is also decreasing for any value of n from 1 to infinity. With those few checks out of the way, let's apply the integral test. Now don't forget that this is an improper integral, so we replace infinity with t and take the limit as t goes to infinity. Now this is set up very nicely to do a substitution where u would equal 2x squared plus 1 and du would equal 4x dx. And that would get us the integral of 1 over u du. Well, I'm going to skip that little substitution here because I know that the antiderivative of 1 over u is the natural logarithm of the absolute value of u. So keeping my variable in terms of x, I know that the antiderivative is the natural logarithm of the absolute value of 2x squared plus 1. And I can double check that by simply taking the derivative and using the chain rule to get 4x over 2x squared plus 1. So now we just need to take the limit as t goes to infinity and evaluate from 1 to t. When we take the limit as t goes to infinity, we have this natural logarithm of the absolute value of 2t squared plus 1. And that is going to go to infinity. This minus log 3 doesn't really make much difference. So we know that this limit goes to infinity, and therefore this series diverges. Now, it's worthwhile just to take a look back at this series and also think about what we could do with the test for divergence. 4n over 2n squared plus 1 does tend towards 0 as n goes to infinity. So the test for divergence wouldn't actually tell us that this diverges. We need to use something like the integral test here to actually determine that it does in fact diverge. Now, the integral test does involve a fair bit of work. There are some scenarios where we might just be able to simplify the series and use what we know about harmonic series and P series to finish this up and determine convergence a little quicker. Remember a few properties of sigma notation here. Constant multiples, sums, and differences. The series of c times an can be written as c times the series of an. And again, if we have a series of two things added together, an plus bn, we can split that up into two separate series. And again, with differences. Let's see how those properties might be able to help us simplify and not have to use the integral test in every circumstance. Here we've got the series 1 plus root n over n squared. Now, right off the bat, we might not need to use the integral test here because we can split that fraction up. Splitting up the fraction, we have 1 over n squared plus root n over n squared. And we can apply that second rule for the series of some sum of two terms. Now, to simplify things further, why don't we write root n as n to the power 1/2, and then subtract exponents. And n to the 1/2 divided by n squared would be n to the negative 3/2, or 1 over n to the 3/2. Now, we can take a look at each of these separate series, and we'll see that these are both P series, and one is convergent on the left, and the other, with P equals 3/2, is convergent on the right-hand side. Now, if we have two convergent series, then we should be able to have both of those be finite sums, and when added together, they would converge to, again, some sort of finite sum. That tells us that the sum of 1 plus root n all over n squared is a convergent series. So really, one of the best results here from the integral test was actually coming up with the proof of the harmonic series being divergent, and also a condition on P series for when they are convergent or divergent. With those things now is sort of just a toolbox of different series. We've got the geometric series with some conditions on where that is convergent or divergent, harmonic series that are always divergent, and P series that are sometimes convergent, sometimes divergent. This will allow you to kind of analyze a lot of series with those kinds of forms with n to a power or some sort of constant to the exponent n. But just for a little bit of curiosity's sake, let's take a look at the harmonic series and how it was proved to be divergent way back in the 1300s. Now, consider that calculus wasn't going to be really invented for another 300 or so years. How did we show that the harmonic series was divergent? It was good to maybe know, just out of curiosity, how things were done back then, because it has to do with a little creativity, and we still need that creativity even today. Sometimes the integral test is not going to be the best strategy. Let's take a look. What we'll do is we'll take each of the terms after that initial 1 and replace it with the largest power of 1/2 that is still less than or equal to the original term. So we'll keep 1 as it is. 1/2 is already a power of 1/2. The largest power of 1/2 that is still less than or equal to a third would be 1/4. 1/4 will stay 1/4. For 1/5, 1/6, and 1/7, the largest power of 1/2 that is still less than or equal to those terms would be 1/8. And 1/8 will stay as it is, since it's a power of 1/2 already. And starting with 1/9, the next highest power of 1/2 would be 1/16. Now, because we've taken each of the terms and replaced it with something that is less than or equal to it, the blue series is greater than or equal to this red series. So we'll move that up there to make it a little easier to read. And now we can actually simplify this series. Keeping 1 is 1 plus 1/2, but starting with these 2/4, since we have 2/4, that actually adds up to 1/2. And we have 4/8 added together, and 4/8 is also 1/2. And you're going to find that we have 8 of those 1/16, and that also ends up being 1/2. And so really we have 1 plus 1/2 plus 1/2 plus 1/2 forever. And we can see that that would become infinite. And that's how we found out that the harmonic series is divergent without using calculus. Just involves a little bit more creativity. That gives us the basis for kind of figuring out when various different series is convergent or divergent. It's really mostly just useful right now when we have powers of n, though, or something that you can easily integrate. We'll see lots of other strategies for determining whether a series is convergent or divergent in future videos. Thanks for watching, and I'll see you in the next video.